Good morning, everyone. Today we're going to be looking at lesson 3-1. We're going to be talking about relations and functions. So this is the first lesson of a brand new topic. Just as a reminder too, I want to just kind of let you guys remember that on Tuesday, we're going to be finishing up our tests. So you'll want to be studying your review sheets that I sent home with you and make sure that you are prepared for that test on Tuesday. So let's go ahead and get ready for our lesson today. The first block up there, you notice there's a lot of different shapes in there. We're going to use those just to fill in the different terms that we're going to be identifying throughout the lesson today. It doesn't matter what order you put them in there. I'm just going to put them in order. They're listed more or less in alphabetical order, but it doesn't matter. You can choose to put them wherever. The first term that we're going to fill in is the word continuous. Oops. The second one is discrete. Make sure you spell this right. This does not mean discrete as we normally use it. This is a mathematical term when we're dealing with a domain, which we'll talk about in just a little bit. I failed to put enough shapes in there, so let's put domain and range together. We'll put function in one of the shapes. We'll put relation here. And finally, in the last one over here, put 1-to-1. Okay, we're going to start by looking at the first example. But before I do that, let's just look at the objective at the top of your paper here. At the end of this lesson, the goal is that you'd be able to determine whether a relation is a function. We're also going to be taking what we learn, like we have been normally in this curriculum, and applying the mathematical part of this to an actual word problem, a real life situation, so we can see how this relates to real world problems. Okay, so the first thing we want to know is how can I recognize a domain and a range? What are the domain and the range of a function? So we're going to fill in this. I have the chart there for you. You just need to put some numbers in there. Put X and Y as you see that I did in the shaded boxes. And then across the top, 1, 2, 3, 4, 5. Across the bottom, 11, 12. And then we're going to write 13 3 different times. And then we're going to identify, first of all, what a relation is. You have to understand what a relation is before you can understand what a function is. A relation is simply a set of ordered pairs. So in case you didn't notice, I'm going to pull that out right now. What we just filled in over here is nothing more than a set of ordered pairs. How can that be? Well, I have an X value and I have a Y value. So if I were to write those as an ordered pair, for example, the first one would be 1, 11. Those are simply points that you can plot onto a coordinate plane. The second set of points is 12 and 2. 2 and 12. I said that backwards. 2 and 12, where you have an X value and a Y value. So that's all that these are in this chart are considered ordered pairs. X, when we're thinking about a function, I'm going to bump down here for just a minute and I want to show you. We talked about this last year, but I found this cool little picture of a function machine. We talked about if you have an equation or a function, we will say, for example, if we were looking to find out something like this, if the rule is 2x, we know that that means every time we put in a value for x, for example, let's say I put 3 into my function machine, it's going to go inside here, it's going to shake around, it's going to plug itself in for x, it's going to shake around, and it's going to give you an output. What is the output here? Well, 2 times 3 would be 6. So 6 is what's going to be spit out. This is always your x value, and this is always your y value. Okay, and we talked about that last year, so that part shouldn't be new. But let's go back up here. I wanted to just kind of throw that little reminder in there so that we can think about it as a function machine. So what you're doing, your x's are always considering these are your inputs in a function, and then it spits out of the machine your outputs. Inputs and outputs. A function is simply a relation. Now remember, All of these numbers in this chart that you see listed out here, this is called a relation. It's simply a set of ordered pairs. The function part is when the relation, what we're going to write here for this is it's a relation where each input is assigned to exactly one output. Sometimes we have a relation that ends up being a function, and sometimes the relation ends up not being a function, and we're going to look at when that is so today. But let's fill in what this is. I didn't probably give you enough room to write the whole definition, so you might have to squeeze it in here, write kind of small. A function is simply a relation, which remember is the set of ordered points where each input is assigned to exactly one output. Okay, that's what a function is. Each input is assigned to exactly one output. We're also going to learn a new name for our first row of inputs. That is called the domain. A domain is simply the set of inputs, which we also know is our x values. The range is the set of outputs, which is simply our y values. Okay, so when I look at this relation over here to the left again, x, all those numbers on the first line representing x is called the domain. So I'm just going to put it right here, the domain. And all the outputs represent the range of our function. Okay, so let's decide how do we write the domain of this function. We take and we look at our first line up here of x terms. We identify all the numbers and we're going to write them all down. Now, if I had any repeating numbers, I only need to write that one time. Typically, we like to write them in order. So we'll put 1, 2, 3, 4, and 5. They're already in order for us. The range is going to be our y values. So we have 11, 12, 13, and I have 13 two more times, but we don't need to write it every time. We just need to write it one time. So there's our domain of our function and our range of our function. Now, let's look at the next part. How do we interpret this when looking at a word problem? Well, imagine yourself standing at a swimming pool that will hold 10,000 gallons of water, and you're standing there with a hose and you want to fill that 10,000 gallons of water, and you're trying to figure out how long it's going to take to fill that pool. Maybe you have an appointment you need to get to, but you don't want to leave the hose run all day, so you got to figure out how long it's going to take to fill it so you know when to start it so that you can make it to your appointment on time. Okay, just imagine that scenario. Here we're told we have a hose that fills a 10,000 gallon swimming pool at a rate of 10 gallons per minute. So that means that when you're standing there with that hose, every minute that pool is going to fill up 10 gallons, okay? So in 2 minutes, it's going to have filled up 20 gallons. Now you could sit there and figure that out all that way, but that's kind of the long way around, right? So if we knew how to assign our x and y value to this word problem, we could simply use our rate. We've been talking in topic 1, we talked about rates, how long it takes to fill a gas tank, how many gallons to put in, how fast. Remember the problem about the bee flying to the garden? Those were all rate problems. So in this case, if I can assign x, which we always know is our input value, which now we know is our domain, we need to figure out, well, what is the domain representing here? And we're going to do the same thing for what spits out of our function machine, which is called our range. And we want to figure out what is y actually, what's going to represent y, or what is y representing? Well, in this case, ask yourself, you're wanting to know how long it's going to take to fill the pool, and maybe at different levels. Because remember, like I just said a moment ago, you will fill 10 gallons in 1 minute, 20 20 gallons in 2 minutes, 30 gallons in 3 minutes, and so on. So there's a function, a rule that would be inside that function machine that for every X you throw in there, it's going to calculate it and spit it out. So we could figure out for different levels of the pool how long it's going to take for that pool to fill. So X is going to be representing the time, the number of minutes it's going to take to fill the number of gallons in your pool. So the domain represents the number of minutes and the range represents the number of gallons. Now let's go over here and look at this one. Here we have a restaurant that needs to order chairs for its tables. We know that one table can accommodate 4 chairs. What is a reasonable domain here? Oh, let me go back over here. I'm sorry. So we wanted to talk about what a reasonable domain is here. So look down here where it has, I failed to read this to you. I want to make sure I read this part to you here. A reasonable domain for that situation with the swimming pool is from 0 minutes, right, from the time you turn the hose on, 0 minutes of the time that it takes to fill the pool. So a reasonable range would be anywhere from 0 to 10,000 gallons. So we start, a reasonable range is anywhere from 0 minutes to however long it takes. We don't know how long it's going to take to fill the pool, right? So our range includes 0 minutes to however long it's going to take, whereas the range, it does have a cap on it because we know the pool can only hold 10,000 gallons. So it starts at 0 gallons because there's not a drop of water in there when you start, right? You're putting the first drop in there. So the range can go from 0 to 10,000 gallons. That's considered what we call, we're talking mostly about what they wanted to know here was, oh yes, it did ask for the reasonable domain and the reasonable range. Okay, so let's look at the restaurant example. All right, so a restaurant needs to order chairs for its tables, and we know that one table can hold, accommodate 4 chairs. Well, a reasonable domain is going to be starting with 0 tables. If you have no tables in there, you need no chairs, right? 1 table, you're going to need 4 chairs. 2 tables, you're going to need 8 chairs. So you have to ask yourself how many chairs are going to be needed for a certain number of tables. And that question is right here. That's what you're trying to think in your mind. So my X, which is my domain, is going to be representing the number of tables needed, or the number of tables that there are. We'll go ahead and put needed. And then it's going to spit out your Y value, which we said is the range. And Y would represent the number of chairs you need. So in other words, if I know how many tables I have, I can figure out how many chairs I need. So what's the reasonable domain and range? Well, a reasonable domain, in other words, what they're asking here is what could X be and what could Y be? What's reasonable? Like I'm not going to say a -5. -5 can't ever be X in this problem because you can't have a negative number of tables, right? What does that mean? Are they buried underground? No. It means 0 is the least amount of tables that you can have. I could have no tables. So my reasonable domain for X could be 0 up through the number of tables I need. And a reasonable range would be simply from, and I like this, well, let's underline this in the problem. So the reasonable domain is from 0 tables to the number of tables needed. And a reasonable range are the multiples of 4, right? From 0 to 4 times the number of tables needed. And that might be a little bit too much to underline, so I'm just going to pull out what's important here. The reasonable domain is from 0 to the number of tables needed. Reasonable range would be multiples of 4 from 0 to 4 times the number needed. I'm not sure I made it too much less, but the point is multiples of 4 because each table can hold 4. So for one table, I would need 4 chairs. 2 tables, I need 8 chairs. 3 tables, I need 12 chairs. So you see, I'm talking about multiples of 4. So as I put in one table into my function machine, it will spit out something in multiples of 4. Okay? So that's what we're talking about when you're thinking about what's a reasonable domain and range. That would be something that we would use in accordance to a word problem where it can't always be every number. X might not be able to be any number you pull out of thin air. You have to think about what numbers are reasonable in this word problem. Now, letter B down here with these other two diagrams that you see, we're looking at just the domain here for each of these. That means we're talking about something about the x value in our set of ordered pairs. Okay, and the terms we want to look at here are continuous and discrete. The one on the left is considered continuous. So let's write down here a continuous domain. We're going to kind of divide this in half. We're going to write about the one on the left and then the one on the right. So the continuous domain, and by looking at this, you can almost see that. That line is continuous. There's no interruptions in it. And the reason that that problem about the gallons of water in your pool would be considered a continuous domain, in other words, the x value is continuous. Now look at what the x value represents on the x-axis. You can see this is time, okay? So we're talking about the domain here, the x values. Okay, they are continuous because the time never turns off. Your hose continues to run for however many minutes it's needed to run in order to fill that pool with 10,000 gallons of water. That is called a continuous domain. So the domain of a function is continuous. Let's write that in here. I'm trying to figure how much we want to write, but we'll go ahead and write this out. The domain of a function is continuous when it includes all, and that's kind of the key word here, real numbers. And it will always make, on your graph, it's going to graph a line, or it might graph a curve, which we haven't seen yet, but you just need to know that it could graph a curve. Okay? Whereas on the problem with the tables and chairs, this is more of a discrete domain. Let's talk about what discrete means. Okay, so on a discrete domain, the reason that this one doesn't have a continuous line is I want you to think about that. Where the water never shut off over here, okay, the time on the clock just kept running. So on this line over here, when we talked about that, every point, no matter where it is on the line, doesn't always mean it's a whole number, right? You could be at 3/4 of a minute, which would be 45 seconds. Okay, so here we're at 1 minute. Let me change the color of my pen so you can see it. Here we're at 1 minute. Here we're somewhere in between 1 and 2, and we're getting closer to 2, but it includes every single point on that line. But on a discrete domain, where we're talking about tables and chairs, we're not talking about points that are in between here. So on the bottom, the domain represents the number of tables, and each one of these points means, okay, so when I have, this is 1 here, I see on our y-axis here we have 4. They're, skip counting these in 4, 8, 12. Okay, so look at this with me. So when you have one table, you look on the x-axis where I filled that in orange, where you have one table, you're going to need 4 chairs. Where you have 2 tables, you need 8 chairs, right? So you see that skip counting in 4s. But there's never any one time where I'm going to have, let's say, if I have 1.5 tables, that doesn't exist. What am I going to do? Saw it in half and then take my chairs and maybe, well, I guess that would mean if I had 1.5 tables, what would that mean? That would mean that I would have 6 chairs, right? But I'm never going to have 1.5 tables or 1 3/4 tables. Restaurants just don't do that. We're not going to saw these tables and then put them together because after all, you're going to lose some of the legs and the thing's not even going to stand up straight. So in this case, you have a word problem that's representing a domain of whole numbers only. So whatever goes into my function machine, the input has to be a whole number, right? That represents the number of tables needed. So it's either 1 table or it's 2 tables or it's no tables. Maybe I have no tables yet, okay? But it can be the domain. So let's write that in over here. Let me get my blue pen back here. So the domain of a function here is discrete when it consists of just whole numbers or integers. And we know that integers means it can include all whole numbers and their opposites, which we know are negative. And you're probably thinking, but you just told me there's no such thing as negative amount of tables. That's correct. So in this word problem, there are no integers that would fit in this particular word problem about the tables. But there might be other word problems where you could have a discrete domain where it could be a negative number. Okay, and that would be, I'm thinking about, gosh, I can't even come up with an example, and I'm not going to worry about that, but you just need to trust me that there may be a word problem in time that you would see where the number going into the function machine could be a negative number. It just wouldn't be representing things like tables and chairs. Okay, it might be levels of something like maybe the water in a bathtub that's going down. Perhaps we would consider how much a temperature could drop or something like that. Okay, so sometimes the domain could be discrete and it could be a negative number, but in the case of our tables and chairs, it's positive. Okay, now let's look at example 3. Now we want to know how to classify relations and functions, and this is really one of the crux parts of the important key parts of our lesson today. So we want to ask, is each relation a function and that's given here in A and B, and if so, is it a one-to-one or not? Is it not a one-to-one? Okay, well remember we said a relation is simply a set of ordered pairs. So in A you see 4 sets of ordered pairs there, 1, 2, 5, 6, 7, -1, and 8, 0. Well, let's look at that. What we want to do is we can write out a little mapping diagram, which you see in letter B. It gives you a little better illustration of how to match up those pairs of numbers. So I'm going to write over here. Whoops, put my hand on the screen and it went wild. So off to the right here, go ahead and write with me. We're going to do a little mapping diagram. We're going to list the domain, and we're going to list the range. And this is kind of what you see done in letter B for us, but many times it's not given to us already in a mapping diagram, so we have to take our points and go ahead and map those out. So the domain, remember, is simply the x value of our set of ordered pairs. So we're going to list those, and generally you list those in order. It looks like these are actually given to us in order, or a domain at least. So let's go ahead and write those out. We put 1, 5, 7, and 8. All right. Now, the range is always the y value. So let's go grab all of the y values, and those we'll go ahead and put in order. I see we have -1. We have 0, 0, -1, 0, 2, and 6. Okay, so there they are in order. From there, we're going to go ahead and match those up as they are in their ordered pairs. So the first set was 1, 2. So we're going to draw an arrow to 2 from 1. The next set is 5, 6. So let's take our pencil and go from 5 and match it up with 6. We have 7 that goes to -1, and we have 8 that goes to 0. Okay, now let's go back to the definition of a function, which we wrote about in the very first example. A function is a relation where each input is assigned to exactly one output. So let's look at this. Each input, which is all of this, is assigned to exactly one output. Is that the case here? Yes, it is. So A is, in fact, a function. So let's write yes, it is a function. And the second question was, is it one-to-one? Well, it is a one-to-one because as you see in the diagram here that we mapped out, each x value has a match to only one y value, or the domain matches, each input of the domain matches only one or exactly one output, which is the range. So this is what we call a one-to-one. That's what letter A is. Now let's look at letter B. Letter B, this set of ordered pairs must have looked like this. We have 1, 17. We have 2, 17. We have 311, 410, and 510. You don't have to write those down. If you've already started, that's fine, you can. But I wanted you to see that those were simply ordered pairs that were taken out and put into a mapping diagram for you. Okay, now I'm going to get rid of them here because we don't really need those there. But I wanted you to understand that that's what that is. So this is your domain and this is your range. In other words, your X values are your domain and your Y values are your range. And each one of these inside those boxes are called elements. So 1, 2, 3, 4, and 5 are elements of the domain, and 17, 11, and 10 are elements of the range. Okay, now, how do we look at this? Because I noticed that 1 maps to 17, but so does 2. So does this fit the definition of our function? Let's go back up and look at that again. Definition of the function says it's a relation where each input is assigned to exactly one output. Let's look at that. Is that true here? Is each input assigned to exactly one output? It is, isn't it? Because 1 is assigned to 17 only, 2 is assigned to 17 only, 3 is assigned to exactly one point element in the range, which is 11, 4 is assigned to one output, and 5 is assigned to only one output. So this is also a function, but it is not a one-to-one. Why not? Because you notice that 1 and 2 in the domain, those elements are both going to 17. So although it's a function because it does meet the rule or the definition of a function, it's just not a one-to-one function. This might be called a many-to-one because you have the 1 and the 2, you have many elements of the domain going to the element 17 that's in the range. So yes, it's a function, but it is not a one-to-one function. So let's write down what these mean here. For A, we said a one-to-one, and I want us to know what a one-to-one means. So one-to-one is where each element in the domain, let's just put a capital D, if you know what that is. Each element in the domain maps to only one element in the range. And letter B, we're going to say not, and underline that. And you can just put 1 to 1 if you like. This is where you would have more than one element in the domain. We'll put a capital D again. Maps to a single element in the range. Okay, both are functions because each element in the domain maps to only one element in the range. Okay, it's not one-to-one in B because it maps. We have 1 and 2 that map to 17, and also you notice that 4 and 5 both map to 10. Okay, and you're going to see why later, maybe trying to remember if there's a problem in there where you see where we don't have a function. Let's look at example 4. Let's identify the constraints on this domain. So what does that mean? So we have a problem here. Let's kind of look at what this says. The diagram shows shipping charges as a function of the weight. So this represents weight over here. Let's fill that in. This is the weight. Weight of what? Of several online orders. The weight, it's bigger. The weight of orders that you order online in pounds. Based on the situation, what constraints, if any, are on the domain of the function. And what's on the right-hand side represents shipping charges. So you know, I don't know if you've ever ordered anything online, but if you do, in most cases, you have to pay for them to ship the box to you. If you're a member of Amazon Prime, you don't have to pay for shipping in most cases. Shipping is free. However, many things are not set up that way, and you have to pay for them to ship you a box or whatever, a package. Okay, so that's what this is talking about. So in the orange box represents the weight of the package that you're ordering, and then the blue box represents what the shipping charges are when it weighs a certain amount. Okay, constraints, that's a word we need to kind of think about. What does a constraint mean? A constraint means limitation. Okay, so the question here is, are there any constraints on the domain or any limitations of what X could be? So when you're thinking about that function machine, what can X be? Can it be any number? Could my weight be 3,000 pounds? I suppose if you're ordering an elephant and a half, right? Or what's an elephant? About a ton? So depending how big your package is going to be, I suppose it could be a lot of weight. 2,000 pounds is a ton. I guess if I was going to order an elephant, I'm going to pay for them to ship 2,000 pounds to me. That's going to be a humongous cost to ship. But if I was going to order some makeup or something or clothing, then the shipping cost wouldn't be as much because it's going to be a smaller package. So let's think about that. So what could X be? What could the weight of my package be? Could the package, because remember, this is our domain, and this is what we're talking about here. Are there any constraints on my domain, on my X value that I'm going to put into my function machine? Could my package be -3 pounds? Probably not. Would my package be 0 pounds? Probably not. So what can my domain be? Is there a limitation of numbers that I could choose to put in the function machine in relationship to this particular problem? Yes, there are going to be constraints. An order that I make must be greater than 0 pounds, right? In order for the domain to make sense. So let's write this. An order must have weight that is greater than 0. Therefore, or so, the domain of this function that we're talking about over here is confined or limited to values greater than 0. Okay? So sometimes you're going to be asked, well, what can the domain be in this situation? Because it wouldn't make sense. Again, this is kind of like the one that we talked about when we were talking about values of our tables up here, right? We can't have a negative amount of tables. It's kind of like that. So the constraints here on this particular problem are that the weight has to be greater than 0. Can't be anything less than that. Okay? I'm going to let you guys try the problems down here, but I need to give you some numbers to fill in. These actually come right out of your book, but I'll give you these to fill in. I'm looking in your book. If you have your book and you want to look at the try it problems on your own and fill them in, if you want to sign off, you can go ahead and get those. But if you want to stick around for just half a minute here, I'm going to give you that information. The try it problem, for example, 1 happens to be on page 89. And there's 2 there, A and B. So you'll see this at the bottom of the page, but here's what you're going to fill in. So we have X and we have Y, and the numbers are 2, 3, 4, 5, and 6. And the range is 0, 1, 2, 3, 4. You're going to list, remember, the domain and the range. If you don't remember how to do that, go back up to example 1. And then the second problem, this should say B, is -3, -1, 1, 3, and 4. And 1, 3, -2 is the range, 2 and 6. Okay, so figure those out. Let's see if you need anything else. I think everything else you can get from the book. I just 102, fill those in. Okay, so try it problems on your own before, if you're coming to Zoom, it's at 2 o'clock today. I have an appointment this morning, so I can't be here this morning, so we'll make it for 2. That'll give you guys a chance to really get a good start on this. I'd like you to try some of these problems on your own, all of them really, before coming to me. It's always good to struggle through and see how many you can do on your own. You have 2, 4, 6, 7, 8, 9 problems assigned from the book. And the try it problems, there are 1, 2 in the first try it, 2, and then you've got all these ones off to the right here also. So go through your book and find those try it problems, give those a shot by looking at your notes above, and then try the lesson problems as well. If you absolutely are stuck, then bring those problems to the Zoom call at 2 o'clock, and I hope to see everyone there today. Please remember that you will be studying for your test on Tuesday, and I will see you all at 2. Have a wonderful morning, everyone. Thanks for watching.